Yeah, all right. Hope I'm audible enough. Yeah. Right. So thank you very much. It's always a challenge being the last person to present on day one, let alone day three, day four. But thanks for staying back and believing that you might get to know something from this presentation, which is quite a mouthful and definitely goes on the raffle for the longest title, I believe. Um, but right, good evening, good afternoon, everyone, and hello to all online. This talk is mostly driven and motivated by something that actually enables a flight software. It may not sound very reasonable to put it already, but definitely from the research perspective side of enabling flight software, it makes sense to actually do some sort of simulations that actually give a direction to develop a flight software. But right before we dive in a little bit about whom are you listening to. So yeah, the names. Right. But yeah, I am currently a doctoral student at University of Tartu, and my affiliation is with Tartu Observatory, which is in Estonia, with a beautiful scenic picture of being in a Baltic country. I'm definitely not disappointed being here, even if the weather was as disappointing for others. But right, that's what my view is for most of the time of the year, about 7 months, and doing space in such challenging environments. That's always a pleasure to be there, and then also to be here to let you know that such a place exists. Uh, Right. So this research direction of mine, which is based on also personal motivation and research perspective, is based on the entire concept of the development of space missions, which includes flight software development and all the other co-ops and operation feasibility planning that includes. But mainly the focus is how can we use and leverage this opportunity to understand how dynamic system works in space, and how our transient events, how can we actually potentially map transient events. And a lot of this is based on these optimalities that space offers, in a way that there's very limited budgets, and especially when we're trying to study objects which are likely to move at very high speeds and high velocities, including comets, magnitudes of kilometers per second. And do we actually have this onboard capability? And can our GN and C suite, and also flight suite, can actually handle such optimal solutions? But also, as we see a lot of these transferability of technologies, it's quite evident that a lot of development that happens in space is also quite applicable in the terrestrial context, and that's where this capabilities and technology transfer is quite viable and feasible. So the general motivation comes from studying objects that have not been visited yet, and these include pristine bodies which we have encountered in the past. Some of them have been identified, not necessarily characterized, but definitely have been tracked to an extent where we may know that such things exist, and the possibility of them coming close to us is also not out of hands reach. But of course, this also comes with the fact that um, while these bodies potentially coming out from the solar system are also have never really been in the influence of our own sun, and hence the um, endogenous properties may not be very well altered, and hence these are good opportunities for us to study them, and hence develop solutions that are able to either correlate with their trajectories, or intercept, or even be companion spacecraft. But all that depends on how the flight software is actually developed in order to able to achieve this. Right. The challenges are obviously well known. Space is very challenging. There's always a problem of sunlight. There's always a problem of velocities, very dynamic environments, dust, micrometeorites. But of course, these all are very potential when we come to actually solving these problems using scientific goals which are identified for the flight software. Although it is quite a challenge when it comes, but heritage missions have shown that we are capable of doing it. But then when it comes to bodies which have not been explored, or which host characteristics that are really difficult to define via simulations, then we require tools that go one step ahead, even for um, to sort of upgrade monolithic flight software codes. In the aspect of what currently exists, we've demonstrated quite well using the numerous boundary value problems and estimating orbital states, initial and final, and we're able to interject with trajectories which involve us to go close to study these objects. And a lot of these simulation tools already define the premise of how we can sort of um, mitigate the possibilities of actually missing a target, but and also increase the chances of actually studying the target from close proximity. However, when it comes to pristine bodies, which is also the one of the targets of this research to develop trajectories and flight software, it is important that we consider the use case not from single agents but also multiple agents, and which is one of the foundational pillars of my doctoral study, which we utilize the essence of using multiple agents to actually explore and develop trajectories that might actually go and explore these bodies. And um, when it comes to developing trajectories for bodies which haven't been, sort of mapped, or we don't know much about, then it's also essential that we do some sort of multi-point mapping, which is able to sort of um, characterize events that may happen on the body or around it, and what kind of environments do they host. A lot of it corresponds to utilization of in situ resources, which we may be able to understand when the event actually occurs. And of course, there's a lot of potential scope of combining domain knowledge, for example, in this case, from the robotics community and from the space technology domain, to advance quite many space exploration techniques. Right. So diving into the methodology, it is based on the fact that when we need to develop trajectories which are to be governed by the flight software, then we need some form of technological readiness, which kind of is the premise for this research work as well. And we use some sort of approximations always. That's quite a possibility before we actually fly, but in this case, we develop these non-heuristic asymptotic solutions to actually develop trajectories. And uh, that's just an illustrative example of OpGrav. Also, credit to NASA and JPL for developing such a concept where we are also able to map gravity. But that lays the premise of one of the um, scientific returns that this research holds in. So the objective constraints are mainly dealing in measuring the gravitational potential at this moment, and trying to maximize the knowledge of the potential, and minimize the distance of encounter. So considering safe encounters when we're developing these trajectories. And for a high level concept, it and this is just a pretty painting a pretty picture of what it could be. And it's always the hope that um, developing the algorithms for single agents flyby is also quite scalable to multiple agents. Never happens Hasn't happened so far with my research, and it's still a um, palm on the forehead sort of a situation, that why doesn't it work. But yeah, um, that's just my testimony. I still have hair on my head, so things are still okay. Um, right. So this is a simulation of what has been developed so far. So considering state of the art technologies that the robotics community offers, using exploration techniques, in this case rapidly exploring rapid trees, and modifying the software architecture to consider the spatial extent of exploration, we are able to sort of explore these bodies. And what you see is the small gray dot is basically the target. We sample a trajectory that flies by the object, and is able to also accommodate the one node that goes away is the one that is actually accommodating for the gravitational influence, which is actually pulling it closer. So we're moving away. And um, as rugged as it may seem, the optimization happens in a way that we are also able to do it for multiple agents on a smoother trajectory. So it's easier for propulsion systems to actually accommodate. I would love to see a spacecraft that moves like this in space, but yeah, we need to also obey physics to a certain extent. Yeah, but then of course the simulations require the flight software requires this simulation readiness, which in this case is explored with a lot of Monte Carlo simulations and trying to optimize and map as well. So it's former SLAM, but it's more like motion prediction and also relative mapping when it comes to moving across space. And we know that we can actually intercept the target at what you see is the bright red star there, and optimize it using the gravitational potential. Um, if I leave aside all the pulling ideas, the optimization worked really well. We got the force solution, and a very optimized trajectory, and uh, it worked for multiple agents as well. There was a whole different story how I got it working, but it works. Um, so this is for three spacecrafts, the singular one and three other spacecrafts flying in a pattern which is which avoids collision, and is also able to um, pass the target at different uh, optimal locations, so that we actually get force measurements that we would like to see and observe, and hopefully can be ported directly into the flight software when it comes to test bed testing. Um, from the part of mapping, we see that if we consider this to be a remote-based measurement of the gravitational potential exerted by, for example, a small solar system body, this is kind of an advertisement for using multiple agents when it comes to exploring such. So, um, considering a single agent sort of an exploration and a multiple agent map, we are able to also kind of concentrate the gravitational potential at points where we were able to actually highly understand where the event happened, as well as to generate a very high fidelity map of such targets. And I hope this plays. It's supposed to be a GIF, but well, that didn't. Oh, it actually did. Okay, I have to click. Right. So this is a sort of a time lapse of how the body moves through space. Um, the spacecrafts running the trajectories were able to concentrate where it found the transient event action, and maybe a little difficult here, but the brightest spot of yellow is where the actual interjection and flyby occurred, and that's where we are able to understand the gravity map at a very high um, sort of guarantee of understanding. A part of my previous work deals with the same sort of trajectory analysis and flight analysis using in orbit gravimetric measures, where part of it also introduces the spacecraft in the gravitational extent of the body, and with very little prior knowledge, just the idea of where the spacecraft is, and the algorithm is able to also repair its trajectory. So starting from a very erratic sort of a motion, as you can see, it sort of um, develops a very smoother curve, which is important for any spacecraft propulsions to be able to handle such non-erratic guidance controls, basically. But these are also useful when it comes to optimal location and tracking. And part of this is developing these simulation environments where the flyby of Oumuamua was modeled, and these spacecrafts eventually end up using the flight software or the flight solution to be able to optimize their locations and develop 3D models of what they saw. So basically, a greater understanding. So it's not just with gravitational potentials, but also to understand the surface dynamics of how these bodies would be. So in case if we have, hopefully, another Oumuamua passing safely from the Earth, a part of this could be reproduced in order to get more high fidelity data when it comes to surface reconstruction, for example. As a part of the study, of course, it's also useful when it comes to understanding how can these be translated into the terrestrial extent. And um, a very nice example in Iceland, where it's supposed to be a very highly dense environment. I loved how people were barbecuing in the volcanic ash. Um, so that was fun to see. I wasn't physically there, but the news articles are amazing. So I invite everyone to to just go and read. And there were picnics, and yeah, I thought it's good for my study. Others thought it's good for a picnic spot. So it was amazing to see that. But I also used this opportunity to gather a lot of data, which was not planned as such, but sort of fitted right into the algorithm, mostly going as an inverse engineering, where we had the data and then we sort of developed the algorithm. So it's both forward and backward propagation of understanding the event. And as you can see, the lava is flowing, quite nice. Yeah, people enjoying it like a swimming pool, basically. But using such trajectories, we're also able to develop the 3D models that very closely relate to what the actual event was, and you're able to sort of see the different hotspots of where it's cooler. The yellow spot is the warmer place, and the red areas are where it's starting to cool off. So understanding such events in the terrestrial occurrences are also quite useful when it comes to actually porting such sort of solutions, maybe to avoid catastrophes, study geysers. I hope I get some data set from Yellowstone geysers, and yeah, could do that. But um, as a part of the verification and validation process, we can also generate what we call as these photorealistic events. Same thing happens on a drone, has been ported to identify and characterize and also localize a potential forest fire using some form of semantic analysis, and develop trajectories on singular events and singular agents and multiple agents, and then develop an entire know-how of the scene. So um, that's where the interportability of the solution is really useful. I also tried and tested it on some simulations from the Didymos and the Didymoon ecosystem, and uh, it performed decently well, where we tried to reconstruct the flybys that happened through the system. Of course, would be great if I could also model the impact and probably test it to see different angles of the plume generation. Right, moving forward, yeah, what I presented are very preliminary results. This is based on I think like six months of work, but the planning has been happening for most of the part of my PhD study. Yeah, a part of it was asymptotic, but I would also like to explore some deterministic solution, and of course get any guidance if any one of you has worked on it, or would like to discuss it. I would be more than happy. But the idea is that we are able to um, assure a guarantee and not just go with an asymptotic assumption, but to make sure that it's actually deterministic. Putting in more perturbation models is always helpful when it comes to multi-agent simulations, and also target bodies, which we do not much really know about, but a lot of it can be also performed in analog environments, which is where we have sort of a space mission simulation center. It's an underground bunker at the Tartu observatory premises, where a flyby installation has been developed, and it's a running wire, and the three cameras that we see are basically potentially spacecrafts which would eventually follow trajectory. Um, from flat Earth. But yeah, um, a part of this also is to understand the mathematical and numerical capabilities, and also to sort of analyze how such trajectories and how software solutions might work. Yeah, that's just another screenshot of me modeling the a comet with plumes and dust environment around it, and a small simulation of how a flyby would actually work. Um, yeah. Right. Just to conclude, of course, these challenges are they exist in the terrestrial domain and the extraterrestrial domains both. So the transfer and leveraging such opportunities and challenges works in both spaces. So um, really happy to be able to identify these use cases to explore regions which haven't been explored, kind of study use cases that actually validate the system right before we launch it into deep space, but also to understand how these dynamic events occur, what are the aftermath, and also learn from heritage missions where DART was an amazing example of such a scale, with hopes that we can also mitigate and avoid in case something catastrophic might head our way. And that is all from my side. Thank you very much for your time and attention.